The last session before the paper session is devoted to IBM Quantum, to Stefan Wörner. Stefan Wörner is a principal scientist and manager of the quantum computational science group at IBM Quantum in Zurich. He has a Master of Science in Applied Mathematics also from ETH, Zurich in 2010. He has a PhD in Operations Management from ETH in 2013. The thesis was titled Complex Optimization Supply Chain Management. And the focus, what he's currently doing is focused on the development and analysis of quantum algorithms for optimization, simulation, machine learning, as well as their practical applications, particularly in finance. And I'm looking forward to your talk. Thank you very much.
Yeah, welcome everybody, and thanks a lot for the invitation. It's really great to be here again. Today I will not talk very much about applications and also not about finance, but about our vision to scale quantum computing, to scale today's noisy devices and use them for applications. But it's really more about the capabilities and the second how we build this up. And maybe you have seen last week there was a new application from colleagues of mine from IBM Quantum, and I want to give a little bit of background on how we got there and what we really can do with today's hardware. And I think that opens a lot of opportunities then for applications research to really leverage that. All right, so the biggest challenge of today's hardware is noise. So the first part of that talk will also be on how we deal with noise. And there's different types of noise, different types of errors that can happen. We can have errors in the gates. Gates might not be perfectly calibrated, so they're not doing exactly what they're supposed to do. We can have qubits that just decohere, that lose their states. They can drift. There's readout errors. So like everywhere in the circuit, things can go wrong. So we have to learn how to deal with that. And there are different strategies. First strategy is error correction, where the computation performed in an encoded logical qubit. So during your calculation, you immediately try to detect and correct errors. And the other approach is error mitigation. Here you do the computation in the unencoded physical qubits. And here the errors are not corrected during the calculation, but actually do a lot of noisy calculations, then do them in a careful way, such that you can average them together to get a noise-free result. If you compare this, then this is today means up to what we know today about these protocols, because of course there's also a lot of research. So error correction can correct. Usually you assume it's the Clifford gates plus the T gate. Clifford gate alone, you could simulate this for Clifford gates alone, you could simulate classically. If you add the T gate on top, then this is really like difficult classically and can lead to a quantum advantage. To introduce and to do that, this introduces a very large qubit overhead. And estimations are that you need a few hundred qubits to build one logical qubit. So it's really a significant overhead. And then this essentially is only for the Clifford gates. Then to apply the T gate, this is again very difficult because it doesn't fit into the code, and which is a fundamental limitation. There's always at least one gate that you need to get to universality that doesn't fit into your error correction code. So you have to inject that using gate teleportation, and that introduces another large overhead. So that's that. Then what can you do with that? Essentially anything. You can run the circuit, you can sample from it, you can calculate expectation values, so this is very nice. There's no real sampling overhead, so the overhead is really here in encoding your things, and the overall scaling then becomes polynomial. So with the polynomial overhead, you can exponentially reduce the noise in your system. So this is very, very nice. So the other approach here, error mitigation, if we look at the gate sets, you can essentially apply any gate you want. Qubit overhead, there's none. Now, what you can do with this is usually restrict this to expectation values. So since you said you average over a bunch of noisy results, what you get in the end is an average, is an expectation value. Then the sampling overhead, because you have to sum over a lot of random results, the sampling overhead is large. For precisely, it's scaling exponential. Now you may wonder, okay, simulating a quantum computer is exponential, error mitigation is exponential, why does that make any sense? And I hope that towards the end of the presentation you see that point. All right, and In the next couple of minutes, I want to particularly talk about different error mitigation schemes. And the first one is probabilistic error cancellation. So suppose we have a circuit like that, where these layers, unitary U1, U2, these can be layers, let's say, of C0 gates across the chip, for example. This is what you want to do, maybe also some single qubit gates. Now what we can do is this noisy layer. So there's noise, and the actual noise-free operation we would be interested in. And if we apply this, we always get the noise on top. Now, what would be cool if we could do that, if we could just like implement this inverse noise map, which would just cancel and would get back to the noise-free operation. And essentially this is what probabilistic error cancellation does. And I'll now go through the main ingredients that actually enable that. And the first one is called quasi-probability decomposition. And some people may have heard that already. This is also used for circuit cutting, for example. All circuit cutting techniques essentially reduce to that. And but I think it has originally been proposed in this context of error mitigation. So suppose this operation E is what we would like to do, the noise-free operation. But what we can do is a bunch of noisy operations F. And now what we can do is we can find, if we know F well enough, we can find this coefficient A, such that the sum over all this circuit, if we apply these different Fs, corresponds to the result that we would get with the noise-free operation. And that's nice. We can rewrite that a little bit. So here, right at the left-hand side, it's the same. The only thing we did here is we kind of rewrote these A factors. So what we did is we normalized them and took the absolute value, such that this is probabilities. Then we recover the sign. And the normalization factor, we just pull it out. And the reason is that this M, this can be very large. And instead of enumerating all possible circuits Fi, we just randomly draw some of them and then we average. And so this is the main idea behind quasi-probability decomposition. And the cost of this is actually scaled with this factor gamma. So the larger this gamma, it's also called the negativity, because these factors AI, they have to sum up to 1 for this to be a proper operation and so on. And if they have negative coefficients, then this gamma becomes larger and larger. And the problem with that is that this increases the variance. So if you're interested in estimation of an expectation value, and you multiply this by a large constant, then you need more and more samples to get back to a confidence interval that's small enough. This leads to, there are two main challenges in this whole protocol. The first, if you don't know these Fi's precisely enough, like if your description of these noise operations is about the same quality of your description of this operation, then it's difficult to really use them for any error mitigation, because by applying them, you also introduce a noise that you're not fully aware of. So characterizing this is actually very difficult. And I think this is also why this paper here is from 2017, why until today this has never been really used at scale. And the second overhead here, or the second challenge, if we apply this a couple of times for multiple gates that we want to error mitigate, then this gamma factor here, this is actually multiplicative. So we have exponential growth of the variance, meaning we have an exponential growth of the number of samples we have to take to get back to a reasonable confidence interval. This exponential growth is essentially what I mentioned before. This is where the exponential cost, the exponential sampling overhead of error mitigation comes from. Right, this is ingredient 1. Ingredient 2 is called Pauli-Treving. So this is quite important here. This is the Lindblad master equation. So this is the equation how you would describe a noisy system. And this is pretty complicated, and you also don't really know how to learn these things from a noisy system. So it's not so clear how to get that and then how to mitigate things from there. However, there's a simpler noise model, Pauli noise, where essentially the only thing you do is you throw in Pauli gates. What that means is, so there are 4 Pauli gates, there's identity, so nothing goes wrong. There's the X gate, it's just a bit flip error. There's the Z gate, which is a phase flip error. Then there's the Y gate, which is both phase and bit flip error. This is everything. And then you can have that on every qubit, and there can be correlations and so on. So this Pauli noise model is significantly simpler, and it will be described with just the probabilities of these different Pauli errors happening on different qubits. Now, this is the real noise model. Why do we care about that? This is now because of Pauli twirling. What Pauli twirling does is essentially we throw in random Pauli gates. So if you look at that example here, let's say this is our circuit we want to run, knowing not to focus on a single T0 gate. Then what we can do is this circuit with some noise. And then we throw in here these Pauli gates. It can be the X, Y, Z identity. And then what we do is we choose here, again, Pauli gates, but we choose them in such a way that the whole circuit, if there wouldn't be any noise, would be exactly what we want to do. So such that they act like an identity. In a noise-free setting, they would not make any difference. But in a noisy setting, what's happening is that on average, we do this many times and look at the result, we actually convert a general noise model into a Pauli noise model. So it's not really reducing noise, but it's tuning noise into a model that's much easier to describe. So which is a very, very important ingredient. And now the last part here is a noise learning. And for me, this was really the breakthrough last year from the colleagues here that also allowed us now to scale to larger systems. Because, let's start. So the Pauli model, since there are 4 Pauli matrices per qubit, is still exponential. So to describe that, you would need 4 to the n probabilities. So we make one simplifying assumption here, which turned out that to be reasonable in practice. And this is that noise is local. So it can only happen on single qubits. So we only take about single qubit Paulis or 2 qubit Paulis for pairs that are on this graph here. So for example, there's no correlated noise between this qubit and this qubit. Of course, both can be noisy, but this noise is not correlated. And if you then look at that graph, this is a 127 IBM quantum Eagle device, then this reduces to 271 probabilities. If I counted that yesterday, I hope that's roughly correct. More generally, instead of 4 to the n, the number of probabilities reduces to a quadratic number if we talk about such a quadratic 2D planar graph. Okay, that's the first step. Then what we do is, if we want to learn the noise of a circuit, we learn that layer by layer. So we don't, the noise is now really a combination of the device that you use and the circuit you want to run. So it's the noise for that circuit. And if, for example, you would like to apply all possible T0 gates here, then you would apply 3 layers. Because, like, if you look at that qubit, these 3 T0 gates, you multiply them in parallel. And the color coding here is kind of the 3 layers. So if you apply all T0s that are green, or all T0s that are red, and all that are blue.
Only for connected qubits.
Exactly. Yeah.
Okay, thank you.
If we would apply all these 3 layers, then we would have applied all possible T0 gates that are hardware native. Yeah. And what we would do is we learn for each of these 3 layers, so they all look like that, but T0 slightly different place. We apply Pauli trilling, and we want to learn the resulting noise. How can this be done? So there are, I think, 2 steps to it. The one is we can extract this Pauli noise by only running 9 different experiments. So also it's 271 probabilities per layer. We can learn all of them only running 9 experiments per layer, meaning measuring in 9 bases. This is because the noise is uncorrelated. We can learn, for example, the noise on, let's say, the noise here and the noise here. We can learn them in parallel, right? We don't have to do several experiments to do that. And if you then carefully, again, color your graph, then you find out that for this kind of connectivity, 9 experiments are enough. That's the one thing. The other thing is to get an accurate estimate of this noise. What we do is we don't run these layers only once, but we actually repeat these layers multiple times. And the reason is to get rid of spam errors, and state preparation and measurement errors. Because if you, and this is why the QPD that I showed before as such didn't work, because if you do quantum process tomography and you just want to learn what one particular operation is doing, then, I mean, there's noise. You won't be able to get a very accurate result due to these spam errors. But if you do it like that, the same preparation error you have once at the beginning, and then if you repeat the same layer 80 times, you don't have any state preparation. You just apply this layer, and then you do a readout at the end. So the spam errors are always the same, independent of the depth, and the depth just amplifies the noise you're interested in. Then you fit a number, and then from this decay rate, you can get the noise parameter you're actually interested in, and this offset, because no noise corresponds to 1 here, this offset captures the spam errors. So this is how we can get a reliable estimate of this noise for these different layers. All right, so this is really the key result of this for making probabilistic error cancellation work, is that we can efficiently learn noise for large quantum circuits. So this is now illustrations of these 3 noise maps for these 3 layers to apply all possible duplicates. And what you see here is for the qubits, you have these pie charts, and what they essentially mean is that color coding means the strength of the X, Y, and Z error on a single qubit. And then for the connections, this is again a color coding for the 9 possible 2-qubit errors, like you see that here. XX, YX, ZX, and so on. But it's a very nice representation of the noise in a 127 qubit device. And then we learn that for all 3 layers.
Is that done as part of calibration or after calibration?
No, you have to do that before you run your circuit, but it's circuit dependent. Okay. It's a good question, because we can think about it if we realize that certain layers are frequently appearing from different users. Then we could pre-calibrate that and then just provide that, and then not everybody has to learn the same layers. Okay. So it's possible.
Is the calibration map then stored so that we can retrieve it? Or is it?
At the moment, it's not retrievable. Okay. And I also don't know exactly whether it will be.
Thank you.
All right. Now, back to probabilistic error cancellation. So this is what we would like to do. This is what we can do. What we now can do with this new protocol, we can retrieve this noise map. And we can really retrieve this noise map independent of the operation. And now, since we have that, we can derive the inverse noise map, and we can use a quasi-probability decomposition really to cool that down, to apply this inverse noise and get a noise-free expectation value. Now, there is a catch. I already mentioned that the runtime scales exponentially, and this is kind of how you can compute it. I want to very quickly walk you through that. So first, if we look at the single circuit that is on n qubits, so n is the number of qubits, has depth d, so that's the number of layers. And if we run that at speed beta is the time a single layer takes to run. We introduce this metric called clock circuit layer operations per second. So beta is 1 over that, over the speed of the device. So d layers times beta, this is the time a single circuit takes. And then this gamma factor, this comes really from implementing this inverse noise map using the QPD. And this gamma bar is a kind of a geometric average that tells you how expensive it is to mitigate one CNOT gate. So it's kind of an aggregate number that is a bit easier to grasp. And then, since we have n qubits and depth d, the number of CNOT gates, in this example where we apply all possible CNOT gates, is corresponds to n times c. And since this is multiplicative, we have gamma to the n times c. So this is the total runtime. Now, let's look a little bit at some concrete gamma numbers and give you an idea here. This is some measurements. Here we have 3 devices. It's kind of 3 different generations. And you see how the gamma factor here decreases from 1.038 down to 1.012. And if you go back and plug this in here, I mean, this is pretty close to 1. So this allows you already to do quite a lot of gates. And here you also see what caused some of these improvements. This is from the first to the second device, the improvement of the T1 time, so the decoherence time, which from something like, I don't know, 80 microseconds, the median went up to 200, so quite an improvement. Now, this gamma factor is closely related to the infidelity of the gate. This is what you see here. So we also try to put this into perspective a bit. And this last device here, we translate this, corresponds to this dashed line here. So this is where we are currently. And if we assume that on a day we can run up to 10 to the 8 circuits, this is what we think is feasible to achieve, for example, by early next year, then this is kind of the 1 day threshold. And then if we further reduce this gate error, 2-qubit gate error, maybe to 10 to the minus 3, then we reach that point where we can run 100 circuits. This is the target that we set for ourselves for next year within the day.
Sorry for that.
No problem. If this error reduces further, then you see that either we can run deeper circuits, or we could run larger circuits and so on. So then, since, I mean, exponential growth is exponential in both directions, right? I mean, it's growing here, but it's also quickly dropping in this direction. So any improvement here, further down, leads to a significant improvement here. Okay, so this is error cancellation, and this is a very nice theory, and also has been demonstrated already in practice, but this gamma factor leads to significant overheads. And there's a way to really reduce that tremendously. And this is by zero noise extrapolation. So what the idea here is, it's difficult to reduce the noise, but maybe we can amplify it. So what we do is we run the same result at the original noise level, but then also at amplified noise levels. Then we have different data points, and then we can extrapolate to the zero noise limit. This is the core idea. Originally, this has been introduced with pulse stretching, so we really calibrated new gates that had more error and so on, and that was led to nice experiments. But this is very expensive to scale. If you have to calibrate multiple gates at multiple noise levels, at the end you are only calibrating with no time for calculations anymore. Then another approach here was to insert noisy gates. So if you replace one C0 gate by 3 C0 gates, by 5 C0 gates, this is logically equivalent because 2 C0 gates cancel. But if they're noisy, then of course you amplify the noise. That also worked for some experiments, but then for larger circuits, you reach a limit where you are just, you have no signal left, you have only noise. The circuits become too long. So that also doesn't really scale. And now, if we look carefully at what has been done here, is we found a way to really learn that noise, efficiently learn the noise. And in probabilistic error cancellation, we use that to reduce the noise level. And like the circuits, that what this actually does is, we introduced this Pauli drilling, which just throws in single qubit gates randomly. What this does is essentially it's just biasing this drilling. So it's also not making the circuit more complicated. And what we can do with that now is we can actually use the same technique to amplify the noise. And this is very nice because this is now really a toolbox that allows us to learn the noise and play with the noise. Reducing gets more expensive, amplifying is cheaper. So why not just amplify it and then combine it with zero noise extrapolation. And this significantly reduces that overhead and led to this result that you might have seen last week, which is titled Evidence for the Utility of Quantum Computing Before Fault Tolerance. And like all the steps that I now discussed, from Pauli drilling over QPD, over this zero noise extrapolation and so on, and noise learning, these are the ingredients that really led to that result. And now I'd like to quickly walk you through the experiments that have been run here and put that a bit into context. So this is using a 127 qubit ether device, IBM Zürich. This is, I think, now also available in our pay-as-you-go model. The problem that they looked at here was simulating the dynamics of the transverse field IC model. So this is a model from physics that describes some simple magnetic phenomena. I think this is not really that important, what exactly that is. And the circuits that they looked into at the following structure, so they repeated the same step multiple times. You can think of that as simulating for longer times. So simulating this physical system for longer times. And every step has this structure. So there's a layer of single qubit gates. They all have the same angle. And then there are these 3 layers of Z0 or ZZ gates. This is more or less equivalent in this context. So they apply all 2 qubit gates that you can apply in the device. And then here you see the twirling has been applied, the amplification of the noise has been applied, and so on to then run these layers and the results. All right, so first 3 experiments here at the top. Those are experiments that could be verified classically. And they were at 5 steps here, so I repeated this thing 5 times. Think about that, it's 3 layers, 5 times is already a depth of 15 with many Z0 gates. This first experiment was looking at the so-called global magnetization. So this is an average over single qubit observables. So you take a single qubit that you read out at the end, and you do this for every qubit, and then you take an average of all these results. But if you carefully look at this circuit, and if you're only interested in a single qubit at a time, then you realize that the result of that qubit does not depend on all 127 qubits, but there's a so-called light cone, and it depends on at most 31 qubits. And 31 qubits you can simulate classically, so that you can easily verify classically. Now, the green dots here, or the green circles, they show the unmitigated results from the real quantum computer. The blue dots, the error-mitigated result. And the black line is now the exact classical result using this light cone argument. And I mean, that perfectly matches, it was very nice. These other 2 lines here, those are from a matrix product state simulator and from an isometric tensor network simulation. And you see that at the beginning, they're doing nicely. And maybe one point, these parameters, so what we see on the x-axis, this is screening different parameters here. Increasing these parameters here, these tensor networks or matrix product state simulators, they were doing worse and worse until they, at the end, they really get it. Another important point here, the first point and the last point, those are Clifford circuits. So these are circuits that we can simulate classically, while the things in between are non-Clifford circuits. So this becomes in general more difficult. Then for the second experiment, this was a larger observable, so you care about correlations across a larger set of qubits. And I think it was 10. And then the light cone becomes larger, so this is 37 qubits that affect this observable. And but this is still something you can simulate. And you see that the blue dots nicely follow this exact line, while the tensor networks matrix product simulator, they, after a certain parameter value here, they really also like deviate from the exact solution. Then the last result here that was still verifiable classically, again a larger, I think 17 or 16 qubit observable, which then results in 68 qubits that affect this final measurement. This is something you can't really simulate anymore like directly, because 68 qubits require memory that's just not available. But there are some tricks that you can further reduce that, and so this was also still verifiable classically. And you see here the matrix product state simulator doesn't cover that at all. And the isometric tensor network, that had also problems that could not even be applied there because it has a worse scaling than the MPS. So with this first set of experiments, this gives a lot of evidence that the quantum computer does actually what it's supposed to do. The error mitigation technique works, and we can run these circuits. So the next step is on experiments that cannot be verified anymore classically. The first one looks very similar to this one, but essentially it has one additional layer of single qubit gates, which effectively corresponds to 6 steps instead of 5. But there's still 16 qubits. But that trick to verify that classically does not apply anymore. So we don't have a classical result, but we know the first and the last data point, because this is Clifford, this we can simulate, and that should be 0 and 1. So we nicely see again that the quantum computer does what it's supposed to do, while the matrix product state simulator here gets completely wrong results. And then this last experiment here, this is now going from 6 steps to 20 steps. So this is now, if you look at that, 20 steps, 3 layers, this is 60 layers of CMOS gates. So those are really large circuits. This is close to 3,000 CNOT gates on 127 qubits. So this is really a big circuit, and here we measure only a single qubit observable, just in the middle, but the light cone is, because of the depth, so large that it's that all 127 qubits really affect the result of that. Again, you have the blue dots. They start here, they go down, and they end up at 0 as they're supposed to do. And again, the classical simulators deviate. And based on the confidence from the other experiments, we of course believe that the quantum results here are the correct ones. But that is not really in the regime where verification becomes difficult. And so right now, we don't know. All right. So to summarize that result, I think the key takeaway here is really that a noisy quantum computer is able to produce accurate expectation values and in a regime where you can't do that with direct simulation anymore, and in a regime where using classical approximations really start to struggle. And I think this is a very nice milestone. And now we have to, of course, see what can we do with that tool. What can we do with it? What are the applications that can profit from that? And the way we make this available is via this is a sampler and the estimator. But the sampler just takes a quantum circuit. You can call that via a cloud API and get back a result. And the estimator takes also a circuit, but also this observable. And because of that execution model, we can put all this error mitigation like behind the scenes, and then have a very easy access model that the user doesn't have to worry about these techniques. All right, so this is now getting towards a tool that can run classically intractable stuff. And I think this is a requirement for quantum advantage, but it's not quite quantum advantage yet. So the question is really, how can we get from this classical intractability to a practical quantum advantage? And there are different approaches, and I think we also will see many more. I just want to give a few examples to give you the idea about what that could look like in certain domains. So the first here is an embedding scheme in quantum chemistry. In quantum chemistry, you can have large molecules, but only a small part of that is really difficult classically. So the idea is that from this large molecule, you only put a small part on a quantum computer, the rest you handle in a classical computer. There might be a large computer, but still classical. And then you need to see how those two really talk to each other, how they together can converge to a solution that represents this large molecule. This is one way how we can, it's kind of a decomposition scheme of a large problem into a difficult part and an easy part, and then use the best resources for these different parts. The other two here are a bit related. The first is entanglement forging. What you do here is you take two quantum circuits, which are kind of independent, and then you classically combine the results such that they represent a larger system. And that makes sense if the two subsystems are like only weakly entangled. If there's not too much entanglement between that, then you can describe these differently and then classically put the results together. Very similar, but kind of coming from the opposite direction, is you start with a large circuit, then you cut it in smaller pieces. This is also an active area of research we're looking into, and that's I think this is very interesting from different points of view. One is from a compiler building, which might for this audience also be very interesting, because this circuit cutting, this of course imposes costs, exponential. Otherwise, you just would cut your circuit into small pieces. But the question of where to cut is not so clear. Different cutting schemes actually impose different overheads. Either you need additional qubits or things like that. And where to place these cuts in the best way, I think, is a very interesting question. It's a question that ultimately I would like to offload to a compiler, because I don't want to do it myself. I want this to be done. And there's essentially nothing like that available. But if it works and if we can implement it, we have implemented it, we have some demonstrations of that already, then it can help to take a larger circuit that might not fit onto the device, cut it into pieces, run it on one or multiple QPUs, then get a result for a larger problem. And like circuit cutting and embedding, of course, can also be combined. That the circuit that you get here is cut into multiple pieces and then run on multiple QPUs. Now, to summarize, today we're here. We can now run really large circuits using error mitigation. And of course, the final goal we want to get to is full error correction. But we think that the transition from here to here is not a discrete one. It's really a continuous one that allows us to use more and more of these resources, or offload more and more to error correction. And here we illustrated that. So you have more like circuits that get more and more complex on the x-axis, and resulting runtime on the y-axis. And classical scales exponential. Error mitigation also scales exponential. But what we can do then is we can combine error correction and error mitigation. Then we have a small code plus error mitigation, or a bit larger code plus error mitigation, until we really get to a full error correction code. And if you look at that curve, then I mean this is a nice smooth transition where we at some point are clearly below the classical runtimes, and then approach error correction. Now you may wonder where exactly are we today. I think also in this curve, this is a nice intersection. This is not a single point in time. Like this is in a fuzzy area, and maybe we entered it now here. But the next thing we'll see is that classical tensor network researchers will challenge these results and will probably improve their simulations, etc. So this is a race now, and this will go on and back and forth until we will clearly be in this domain. With that, I think there are two key questions that we are looking into from an applications point of view. And one is, particularly if you look about this, think about error mitigations, what are the problems that really depend only on expectation values? This is one thing. What are problems that have a structure where this technique can help? As for example, in quantum chemistry. And the other is, what other techniques can we find, or what's promising to really bridge that gap from classical intractability to quantum advantage? Because I think it really requires the best of classical and quantum to get to a practical result. And with that, thank you very much.
Questions? Yeah.
Stefan, thank you for the talk. I speak loud. On one of your slides where you had the 127 qubits in a row, yeah? Then you had many steps. How many qubits do you need? For each step you need again 127, or?
Just try.
You have the picture before. So I'm just for clarification. I'm just want to ask how many qubits you actually need to run that, let's say, many step.
So every single step involves all 127 qubits.
Yeah.
And every single step consists of 3 layers.
Yeah.
And every layer, let's say the red layer, takes all the qubits that are connected to a red edge.
Okay.
The blue layer takes all those,
yeah.
The green layer takes all those. So for every layer there are a few qubits that are not connected, but I don't know the exact ratio, but it should be relatively large. Like I think most of the qubits are used most of the times, and over all 3 layers within one step, all 127 qubits are used.
And then for the next step?
It's just repeated, just the same.
So do you have to, let's say, apostrophes, reprogram the connectivity or something?
No. Because we repeat these steps again and again, it's always the same layers. This is a very good point. Depending on the complexity of your circuit, you might have to learn multiple layers. If your layers never repeat, then of course you need to learn every layer individually.
Okay, thank you.
Thanks for the introduction to voice learning. I didn't get it before the books, but I have one more question to this. How long is this voice model you learn valid for the quantum?
This is a crucial question. Like the exact time, we of course don't know. So I think there one has to run maybe some monitoring experiments also to kind of capture that. But it seems to be in the order of an hour or more.
Ah.
So it is stable for a while, and me being a mathematician, I'm not involved in this calibration stuff, but what I hear from the experiments is that they also changed a little bit the calibration policy away from optimizing every gate individually to optimizing maybe overall a more stable behavior. So it's like a more global point of view versus a local greedy policy.
Any more questions? Thank you very much. Break or something?
We have 5 minutes to have a quick bio break, and then we'll start with the first paper session.
Thank you. That's so.